All right, so last time we got right up to where we were hoping to be and didn't quite get to file systems, but we'll do that today. But first, let's recall a little bit about what we've been talking about, performance of I.O. And among other things, we kind of highlighted a couple of parts of the I.O. One was this queue thing, and the other was device-dependent I.O. Timing that basically depends a lot on what you're using. So if you're using a disk, it's got certain performance characteristics. If you're using an SSD, there's others. And so the performance of the I.O. subsystem really has a bunch of performance metrics that you can consider, such as response time and throughput. And one of the things that we did do also last time, if you recall, was highlight the basic overhead, which is S here in this equation, and how important that is to the actual performance. All right? And this is sort of the effective bandwidth is actually diminished by the overhead. And of course, then we talked about some other contributing factors to latency, such as software paths, which is loosely modeled by a queue. We talked about I.O. device service times. We didn't really talk much about hardware controllers, because that's very dependent on the type of controller you've got, but you've got to remember it's there. And then this queuing behavior thing is potentially a really huge increase in the overall time it takes to service a request, as those of you who have ever stood in a line can attest. And so we talked a lot about this response time versus utilization curve, and as you get closer and closer to 100%, of course, your response time goes through the roof. Now, if you remember, we gave you two very simple equations. These are actually at the bottom here. These are remarkably simple, certainly as queuing theory goes. And they're going to talk to you a little bit more about these in section. But this MM1 stands for memoryless input, memoryless output. And so that's the type of equation that you want to use if you're modeling the output server as memoryless. And then MG1 is if you're modeling the output server as general distribution. Keep in mind that this particular type of queuing theory we talked about, it's always a memoryless input. If you want to do something more general, so you want a GG1 queue, take a queuing theory class. There's a book like this. It gets much more complicated much more quickly. Can somebody remember briefly what it was about memoryless distributions that made them kind of reasonable model in some circumstances? Yeah. So they have a nice bursty behavior. They have a long tail. Okay, what else? Why are they called memoryless? Yeah.
If you know that a past event occurred, it doesn't change the probability of the current event.
That's right. So no knowledge about how long ago the past event was tells you anything about the future event time. That's the key thing. It's memoryless. And basically, think of this as the Berkeley bus syndrome, right? It doesn't matter the fact that you've waited for 10 minutes or a half an hour or an hour. It doesn't have any reflection on how long it's going to take, okay? And so just keep in mind that these parameters here, it's always a memoryless arrival rate, but the service rate can be general, and you can do anything from deterministic on up through arbitrarily complicated behavior. And what's cool about that particular situation is you don't care actually what the shape of the curve of the distribution is at all. You just care what this C character is, which is the divergence square, the divergence over the mean squared. So that's kind of a nice piece. So were there any? And notice, by the way, everybody see this utilization U. It's U over 1 minus U. So as U goes to 1, which is 100%, what happens to both of these guys? They go to infinity. So this very simple model is a way of reflecting this curve I showed you here. Okay? And again, they'll talk more about this in section, but did anybody have any other questions on this briefly? Yeah. Say that again? Oh, yeah. There's a typo there. My apologies. That's an extra parentheses, yes. By the way, notice what happens when C equals 1 and you plug 1 plus 1 divided by 2 is 1, and therefore this equation becomes that one when it's memoryless. So these are really the same equation. The open parentheses is in the back over there by the exit sign. Sorry, that's a typo. It is, by the way, I always find this equation, once you get past the shock of, a lot of terms and stuff, very amazing to me that just the fact that there's randomness on the input leads to that behavior of the the infinite curve there. If you had a deterministic input, you would not necessarily have that problem. So just the fact that there's burstiness on the input, which was the good answer there earlier, causes you to get this queuing behavior. So that is something to keep in mind. All right, I'm not going to spend any other time on this if people are ready to go. Good. So when is the disk performance highest? Well, when there's a big sequential read, or maybe when there's so much work that you can rearrange the work. I'm going to show you that in a moment. And it is kind of interesting that with a lot of these I.O. devices, if things are mostly idle, you can be a lot less efficient than if they're busy, because it doesn't matter as much. Okay? Bursts in behavior are both a threat and an opportunity. They're a threat because the queue length goes up, but they're an opportunity because we'll be able to rearrange those bursts to potentially get better behavior out of the mechanical system. All right, so we're going to show you that in a second. And then, of course, you can put your idea for optimization in here. I like to say that while you guys have PINTOS, which is sort of operating system in its pure form, you go to a real operating system, it's a mess. Okay, why is it a mess? Because it's lots of heuristics, your optimization there, some of which work, some of which don't, and then there you combine that with sort of legacy history and you got a mess. Okay, and that's just the way modern operating systems are. And so that's why we kind of try to give you some ideas in the more pure form so that when you're reading real operating system code, or you take the 194.24, if we ever teach it again, and you're looking at Linux, it's like, well, gee, that's a mess, but I can see buried in there are some of these more pure ideas that we've been giving you. All right, that's part of the reason we do this. And then there's going to be lots of other techniques. I'm going to briefly mention using user-level drivers as a way of getting the service time down. We'll also talk about, maybe overlapping I.O. and computation as well. We've talked about that several times this term. So, click. So let's talk briefly about this disk scheduling idea. So disks can only do, let's say, one request at a time. We said that was basically because of the cost of the heads and the DSP and so on. And so if you have a bunch of user requests that come in, and they're on track 2, sector, whatever, the question is, how do you schedule the disk to do those requests? And there are many ways that you can schedule the disk, just like there were many ways we could schedule the CPU. So for instance, we could take every request as it comes in, send it to the disk, FIFO. Okay, what do you think? What do you guys think FIFO is going to do? It's going to be good or bad algorithm? Okay, probably a bad algorithm. All right, just because you've had such great experience with FIFO up till now, right? So I'm going to show you several options here, just to give you an idea here. And this is going to be our generic picture on the right, which is a disk head, and we're going to ignore the sector number for a moment because that's harder to optimize for. And so here's what happens with first in, first out. Look here's the set of tracks we want to go with. And of course, what happens? The scheduling order is 2, 1, 3, 6, 2, 5, just like they came in. And the head goes down, the head comes up, the head goes down, and the head goes all over the place. Okay, so basically the problem with FIFO is FIFO doesn't necessarily take into account anything about the disk. Okay, and so you hit that seek time on every read. All right, and now of course the pro of this is it's fair, via some odd definition of fair. The cons of this is, of course, that you're basically just going all over the place to random spots of the disk. Now here's another option. We could say, well, instead of that, let's just go to the shortest next step. Okay, so we're now going to take that queue of possible inputs and we're going to rearrange them so that we meet this sort of shortest seek time first. And so here, if we have this set of incoming requests, 2, 1, 3, 6, 2, 5, same as before, perhaps we'll schedule it this way, okay? Because notice that the disk head here is already on 5. So what do we do first? Well, 5 is going to be the shortest seek. Does everybody see that? Because we don't have to go anywhere. And then maybe we'll go to 6 because that'll be close. And now we're forced to go all the way down to 3. And then we'll do a couple of 2s and a 1. So basically what we've done is we've reordered this set of requests to this set of requests. And so now if you look at what the head does, it's much more direct. Okay? So that looks good. Now, the pro of this is it reduces seek, and the overall time to process a set of requests here is shorter, clearly. Is it better? Is shorter better? Who wants to say not necessarily? Go for it. Who wants to say yes? Yes, okay, go for it.
Well, is it because, I think it's because here we're only considering seek time, right?
Yeah.
Isn't there time to read, so it could be that, like, the shortest seek is also an incredibly long read, and so that just, like, slows, like, that just, like, halts the entire process. You need to consider that as well, right?
Sure, okay, you have to consider the read time, yes. But in some sense, look, we did that because we have 2 reads off of track 2, which has got some similarity to what you just said, right? Go ahead.
It's a very greedy algorithm.
Right.
We could follow our nose along a bunch of short seeks, and then end up being very far away from a read that we have to do on the other side of the disk.
Okay, so it's a very greedy algorithm, right? The other thing is it can lead to starvation, right? Because if you have somebody who happens to be way on the other side of the disk and a whole bunch of requests come in at the where you are, you may never get to that other request. Okay? So I guess the real answer, when everybody says, is this better? Okay? That's a dangerous question, right? Anytime somebody asks you, is this better? The first thing you ought to ask is, better for whom? Or better according to what metric? Okay? There's an urban legend, of course, of the standard philosophy class where you go in after a whole semester of discussing deep philosophical topics, and the only question on the final is, why? Right? And, of course, the right answer is, why not? The better, and then maybe a slightly less good question or answer might be something like, what are your assumptions? I don't know. But you really got to ask, what are we assuming here? Now, from the standpoint of the throughput of the whole system, this might be pretty good, right? Because we're getting more requests out per unit time than we would by taking the FIFO example. But this does have this starvation problem, which could be a serious problem under some circumstances. And so this is really failing the quality of service requirement. And so we could do something simpler. Here's what's called scan, which is what's often called the elevator algorithm. And the idea is take the closest request in the direction of travel. So we just kind of go down and up and down and up, right? And if you ignore the way elevators work in both Soda and Corey Hall, this is kind of the way elevators are supposed to work, right? They pick people up on the way up, and they let them off on the way down as well. And this kind of works out pretty nicely, right? Because it goes down and then comes back up. And the pro of this is there's really no starvation. And you get pretty low seek times. The potential con is, if you think carefully about this and observe this the next time you're in a very tall building, is this is actually favoring the middle tracks. Okay, so people who happen to be not on the ground floor and not on the top floor, but are somewhere in the middle actually win a bit because you get picked up on the way down and up potentially. So there is this slight modification, which is called C-scan, which is you do the same thing, but you only go on one request. So it's like you only service requests on the way down, then you go zooming back up, and then you do the same thing. And of course, in this case, this is pretty simple. You just kind of go down and then service on the way up and so on. Okay? So I don't want to go in much more detail on this, but the interesting thing here is that by having a set of queued requests, which we were earlier kind of saying might be a bad thing, we now have an option to do a much better scheduling of the hardware device itself. So the existence of a set of requests to choose from lets us maybe optimize better. Okay? And by the way, modern disk controllers do this internally. So operating systems tend to try to do elevator algorithms in many cases, but they're often competing with the elevator algorithms that are on the disk controllers themselves. And so you can actually have multiple requests that go out across the bus, and then the disk controller reorders them. And so there is that interesting sort of stress there. Okay, are there any questions on these options? So next time somebody asks you what the elevator algorithm is, you have an answer to that, right? And by the way, if you go in the Linux code, there is I/O scheduling, just like there's regular scheduling, and yes, there is an elevator algorithm scheduler in the Linux kernel, so it's there. Okay, so on a slightly different topic, device drivers, if you remember, is that device-specific code that's in the kernel that supports sort of standard interfaces, and it's the part of the software, the kernel, that's very specific to the device. And we talked a bit about how they're structured in terms of top and bottom half and so on. That's not going to be my point here. The point right now is, does this have to be in the kernel? Okay, no. Why not? Because it doesn't. Well, okay. Why would we put it in the kernel? And why is the standard sort of answer probably yes, but doesn't have to be? Give me why somebody might say yes to start with.
Well, the obvious thing is, like, we learned about microkernels, right? And, if you keep them in the kernel, then it's more efficient because you just have to make one call, do what you want, right?
Yeah, so the argument is efficiency for the kernel, and what's the other argument? Good.
What's the other argument? Simplicity, I guess?
Okay, simplicity. What else? What about hardware devices? They're kernel accessible, right? So inside the kernel, basically the kernel has access to everything, and so you might by default assume that you wanted to have a device entirely in kernel space so that the kernel can manipulate all its registers. Of course, when we talked about memory mapped I/O last time or the time before, we started talking about how the kernel could use virtual memory to map the I/O registers into user space. So there's no reason we couldn't actually run things at user level. Okay? And there are different types of drivers. There's kernel level drivers and user level drivers. Kernel level are things that typically are critical devices that you want extremely low I/O to inside of the kernel, and you might imagine file system as talking to disks that way. But in fact, user level drivers are a little more flexible and a little safer, because you put them at user level, the kernel says, well, that user level driver only has access to the registers for USB or for some particular device, and then if it crashes, it doesn't take the whole kernel down. Okay, so user level, and by the way, because you're running a lot of stuff at user level, you don't actually have to make a system call into the kernel to access the driver. So you've just saved the cost of a system call in some instances. So they can be faster. Okay, so the trade-offs are not so obvious here. And so kernel-level drivers have a limited set of resources available from a programming standpoint because they're actually in the kernel, and so you have to be a little careful about when they go to sleep, right? You don't want to go to sleep in an interrupt handler and so on. But they do have access to everything. Okay, so you could use kernel-level threads if you wanted to. User-level drivers are very like other application programs, but the kernel has to have given them special privileges to access the device registers. Okay? All right. So this is actually a trade-off kind of between security and convenience, or security and efficiency, or performance and efficiency under some circumstances. Not always obvious. Not as obvious as it used to be in the old days where drivers were only in the kernel. Okay, questions? Good. Now let's do one last one here. So another advantage of a queue, and by the way, when we talk about reducing overhead, that S parameter, one of the big things we're looking at is service time, because O is kind of the service time. And so by getting the T-SIR down, if you look at the queuing theory equations that I had at the beginning of the lecture, T-SIR directly reduces the queue time. Okay, so if we can make the time to service something faster, then our queuing time goes down. All right? And suppose that every read of something the server is doing, call this a disk, whatever, it takes 10 milliseconds. Suppose a process works 100 milliseconds after each read. What's the utilization of the disk? Okay, well, 10 over 110. Okay, 9%. That's not a very well-utilized disk. So what can we do? How do we fix this? I mean, suppose that this disk was the slow thing in our system we want to optimize for. Yeah. Yeah, let's do 2 of them, right? Suppose we do 2 of them at once. Now our disk is 18% utilized, right? So just by increasing the number of threads, suddenly we've got better utilized disk, which might be the critical resource in the system. Okay? And so why not just keep going? You know, each of those have 2 threads, and there used to be these old Fabergé commercials when, in the old days, they told 2 friends and so on and so forth. Why not just keep doubling the number of threads indefinitely? What might happen? Could we get the disk time to 100% utilization? First thing you should say is, boy, Professor Kuby, I know you told me 100% is always a bad idea, so no. We might actually take an answer like that. But can somebody come up with some reasons why 100% might not be a desirable target here? Yeah.
If your utilization is at 100%, your queue will grow without bound, and you'll stop dropping. You'll start dropping requests on the floor.
Okay, so you'll start dropping requests on the floor. Now, what did we say earlier in the lecture? Any random variation in timing is going to cause that queue growing behavior. Yes. So let's accept that the growth of the queue might be a serious problem here. What are some other problems that might prevent me from getting to 100%, even if there was no randomness in the system? Yeah.
If you have to have a lot of interrupts with the scheduling, you might have interrupts disabled while you're dealing with
Okay, yeah, interrupts might be disabled for too long. See this 100 milliseconds? What's our basic assumption that 100 milliseconds isn't changing as we're adding more threads? But now maybe we don't have enough CPU to have an arbitrary number of threads running, and what happens is no longer is the disk in the critical path, the CPU becomes a critical path, right? So you have to keep in mind all of the resources in the system. Perhaps we get to the point where the disk is no longer our problem, but the CPU is. Does everybody see that issue? Okay. So, now, of course, we already showed you this, right? Several lectures ago. This blocking interface is the standard wait with reads and writes until the I.O. is completed. We gave you a couple of options, like non-blocking I.O. and asynchronous I.O. And both of these are ways to make sure that you can do other things while you're waiting for I.O. to happen. Or, conversely, if you have multiple threads going on, you can basically submit multiple requests to a disk at the same time. So this is sort of two sides of the same coin. Okay, these guys are ways for threads to hide I/O latency. Multiple threads are ways to make a device more heavily utilized if it's underutilized. So you want to make use of both of these ideas. Okay. Questions? All right. So, where are we now? So we've been talking about disks and I/O drivers, so we dove all the way down, and I think today we're going to pop our up a level here to talk a lot about structuring of blocks to make file systems. That's going to be our goal. And if you remember, we had a low-level interface of open, create, close. These are the actual system calls available to us, and for instance, open, it takes a file name and a bunch of flags that have things like what access modes do we want, what open flags, and so on. And the question that you might ask is, what's the return value, for instance, from open? Anybody remember? What was the return value from open? Say, what is that? File descriptor. And what was a file descriptor? Well, it's an int, right? So it's a number. So the file descriptor is what you get back as a user that allows you to further manipulate the files later when you do reads and writes. Okay, and so now we're going to kind of talk a little bit in this space of how you turn a file name and some flags into a file descriptor that you can now do reads and writes on. And what is the underlying structure going to look like? Okay, and here's some of the reads and writes we have available. So when we say read, we actually say here's the file descriptor. So that integer is what came back from our open call. Here's a buffer. Here's the maximum amount of data that can go into that buffer, and what it returns is either the number of bytes read or an error. Okay, I actually saw some traffic on the news group talking about error return calls and things like that. That's always a good way to think. Everything has a return error, so I always be thinking about that. So in this case, read can actually give you an error under what circumstances? When might we get back an error?
If the buffer pointer is not correct.
Okay, it could be problems with the buffer pointer. We might have to validate the address that the user gives us. Yes, what else could be an error? Could be a bad file descriptor. Could be a bad disk. Could be an actual read error, right? There's lots of errors that could come back. So it's always a bad idea to go ahead and just do a read and assume you're going to get your data back. And then, of course, we have things like seeking. Go to the middle of the file. So once we've got seek, suddenly we've got random access. So if you didn't have seek and you only had read and write, you might assume that everything was sequential. That's going to give us a certain structure of our file system underneath that does sequential well. The moment we want to start seeking, like, for instance, with databases, now we want to have a file structure that supports randomized access easily. Okay, so those are not necessarily the same thing. Like somebody give me a really good, fast way of organizing sequential files on a disk. Ignoring all other complexities. What might you want to do if you wanted to do really well at fast sequential access to long files on a disk? What would you do with them? That's right. You just put the file on one track, and then maybe if it's really long, you just keep going, spiraling in or spiraling out, right? That would be a really good way to organize a file sequentially on the disk. Why might we not want to do that? Or what? Let me rephrase this. What might prevent us from doing that? Yeah. Okay, yeah, fragmentation you mean. Yeah, so we could have fragmented space, right? We could have stored a short file and then tried to store a long one. There's lots of things that get in the way, and so our file system access is going to depend on that. Okay, so building a file system, what is a file system? It's the layer of the operating system that transforms blocks into files and directories, okay? So blocks are not something you deal with. You don't think about a block, you think about a file. And so some components of the file system are things like what's the disk management, how are blocks put into files, what's the interface to find a file by name rather than by block. When you find a file, you find, George or /user/homes/George/secret data. You don't find something by number. Yes?
But isn't it true that lately, with cloud computing and stuff, there's been changes, they do object storage or block storage instead of file storage?
Well, so there is a little bit of a transition into the way we think about the objects, but files are objects typically. It's sort of a little bit of what they're optimized for. Your real question, I think, is do people still name files hierarchically, or do they use a database index to look them up? That might be a different version of that question. Hold that question until we talk a little bit more about naming, but it's a good one. Okay? And protection. How is our data kept secure? That's a question. How is it kept reliable or durable? Everybody here, whoever buys a desktop or tower or server, there's no excuse to not have at least RAID 1 so you have replication because disks are cheap enough. Okay, we'll talk more about RAID later in a further lecture, but you might as well have really good reliability against losing a single disk. There's also the user versus system view of a file. So the user's view is a bunch of durable data. The system's view is a collection of bytes, and the system doesn't really matter how the user's using those bytes. Okay, the system thinks of it as a collection of bytes, and then the system's view inside the operating system is as a collection of blocks. So there's a bunch of different ways of looking at a file, and we're going to have to make sure that we have them all sort of sorted out when we design our file systems. All right, and we're actually going to start with something very simple like the FAT file system, which is going to be easy to figure out. So, Administrivia, we finished midterm 1 grading. The good news is that's a really nice curve. The bad news is the average was 56.5. I'm really sorry about that, folks. I usually target like 70 is my ideal average. So this was harder than expected. But fortunately, this is not a 61 class, so we actually curve everything. So I guess that's good. We did say, clearly this exam was harder than expected. We did say that regrades are good up until Thursday. We will be either shutting that feature off on Thursday or ignoring future requests, so you need to get them in by then. And make sure that you want an actual regrade, because in principle, we might regrade other things, so make sure that you're ready for that. We'll look closer. Midterm 2 is coming up. It's 2 weeks from Wednesday. April 22nd, so it's getting close. Going to be every topic up to the Monday before. So, any questions of Administrivia? I don't think I have anything else that I needed. Was there anything else that we're missing? No. It is a beautiful curve, isn't it? Isn't that just... Anyway, mean is too low. Sorry about that. Okay. Yep, in principle it's included. Up to the Monday before. And then anything we miss goes on the final. So, so the midterm 2, as I mentioned last time, is not an everything up to midterm 2 from the beginning of the class. It's everything between the 2 midterms. I mean, it's after midterm 1. And topics that we might have missed on midterm 1 are fair game on midterm 2. But other than that, we're not going to retest you on stuff you learned the first day on midterm 2. Final, we might. Oh, yeah, checkpoint 2 is due today. Yes. I should have put that on there. Sorry. Anything else? Okay. Good. And everybody solved the halting problem like they were supposed to? When was that due? That was due on Friday, wasn't it? Yeah, just kidding. All right. So if there's any other questions, let's talk a little bit about translating from user to system view. So the user's view is a bunch of bytes. No, the user's view is a durable document, and somehow the file system has to turn that into blocks on a disk. And, what happens if the user says, sort of, give me bytes 2 to 12? What are we going to do? Well, we got to fetch some block off of the disk into memory, extract bytes 2 to 12, and then hand them back to the user. Okay? And what does that mean? That means there's got to be some buffering inside the file system. More interesting is, for instance, what if I say write bytes 2 to 12? Well, then we load the block off the disk, fill in bytes 2 to 12, and then write the whole block back, because the only interface we have to a disk is a block interface. And we're going to talk, hopefully we'll get there by the end of the lecture, about caching in the system. There's a lot of caching inside the file system, and it's quite possible that you write your data and it's not on disk yet before the system crashes. Okay, so that's something to worry about. Now, I just said that. Okay, so everything inside of the file system is in whole-size blocks. So, for instance, getC, putC basically might buffer up 4,096 bytes before writing it out, because the block interface is, not a byte interface. So hopefully that's clear to everybody. And so from now on, we're going to dive a little bit deeper, and now a file is basically going to be a collection of blocks that we're going to somehow organize into a file structure. All right? So you're going to design a file system. What are you going to do? Well, first and foremost, you got to know what you're going to use it for, okay? You want to make sure the data is durable, otherwise there's no point. And so in the case of a disk, durability comes because we push it out to the disk. In the case of SSD, durability comes because we push it out to flash. We're probably going to want performance. Okay, most people are not happy if things perform poorly. And so, for instance, we might want to maximize sequential access whenever possible and try to get seeks down. We're going to have this basic philosophy of you open first, and then you do reads and writes on an open file. And the reason for that is actually fundamental, because on open, we actually check, first of all, that the file exists, and second of all, that you actually have permission to use it in the way you want. So the opening process is all about checking. Okay? This is interesting when you think about it, because it says that if somebody breaks into your operating system, what does that mean about the access control on files? So if you got a virus or a worm that breaks in, what about your files? Are they safe still? How many people think the files are no longer safe if somebody breaks into the operating system? Okay, most of you. How many people think otherwise? Okay, why not? So it depends on what permission the virus has, yes. If we assume, though, that the virus is able to get full kernel level permissions, then you can imagine that this philosophy here leaves us open to attack if somebody breaks in and gets kernel level privileges. Okay? Is everybody with me on that? What could we do anything differently? Well, is there some way that we could have a situation where somebody who broke into the operating system didn't instantly have access to all of the files? Read-only memory. Well, but if you encrypt, presumably the key is in the operating system. So if the thing is running and they break in, then the encryption doesn't help you any. Unless you have some way of encrypting the data, then handing it to the operating system in a way that the virus can't see, maybe. Go ahead, yeah. Yeah, so the interesting thing about passwords is they're given to somebody. Maybe they're given to the operating system. So by the way, we don't have to come up with a solution to this, but I want you to start seeing a little bit here that the typical file system interfaces assume that nobody's breaking into the kernel. Okay? I'm going to see if we can have enough time to talk about alternatives, but they certainly involve encryption and some other sort of techniques to try to get around this basic idea. But for now, because we're talking about normal operating systems, the idea is on open, we check all our permissions before we give back the file descriptor, and then we allow reads and writes on that file descriptor. Okay? Size is determined as the user uses it. So when you open a file, the operating system has no idea how big that file is going to be. And then you proceed to write a byte in close, that's a little file, or you write 2 terabytes in close, that's a big file. And the operating system doesn't know the difference between those until it starts seeing all the data. So that's a problem. It's an interesting one because it basically means we need to somehow start small and grow on our files. It's an allocation problem. Okay? And of course, we want to organize into directories. And the reason we organize into directories is so that we can reference files by a path name /root /user /home /whatever. This is interesting because, as was brought up earlier, we're shifting a bit away from this. Okay? How many of you have a disk somewhere that's so big that you can't find anything in it? I don't remember what directory I put that in 12 levels down. right? Anybody starting to get that kind of space? This happens a lot when people have pictures and media and code and my philosophy these days is I just take the data from last year and I put it all up and keep it somewhere and keep next year's data and someday I'll have a petabyte, well, probably not of personal data, but I'll have no idea where it is, right? Okay. But we're going to assume we organize into directories for now. And obviously, since you've got to be able to delete files and create ones, we need to figure out how to allocate in free blocks. So these are all issues that come up when we start saying, what file system are you using? How is it structured? Okay, any questions on any of this? Yeah, go ahead. So a file system, the good question, does a file system have to deal with fragmentation is what you're asking, right? It doesn't have to if it's built correctly. We'll sort of see what some of the consequences of that are. What are consequences of fragmentation, do you think? That's right. So the consequence of fragmentation is lots of short little non-sequential blocks, and so performance goes down, right? Some file systems, we're actually not going to talk about, if we get to NTFS, you'll see this a little bit, but there are file systems where fragmentation leads to the maximum file you can store drastically going down. Okay, so there is that negative consequence on the file size thing, but mostly for the file systems we're talking about, fragmentation is going to be a performance problem we're going to have to fix. Yes. Okay? Any other questions? All right. So basic entities on disk are files and directories. Typically, directories are just files with information in them. Okay? Access the disk is going to be a linear array of sectors. There's a couple of options here. I mentioned this already. We could identify sectors by which cylinder, surface, and sector they are and sort them in cylinder major order and do something with them. Most people don't do that anymore. The other is a logical block addressing scheme, which is typically pulled off by the controller itself. And so the controller for the hard drive actually figures out which blocks are bad and takes the remaining good ones and puts them in a logical order and hands them to you. All right, so while this original cylinder surface sector thing was very easy to start optimizing because you knew exactly kind of what track you were on, here with the LBA you have to sort of make some guesses. Things that are close together are on the same track typically, or adjoining tracks. All right. So, and we need a way to track the free disk blocks, so we could link all the blocks together. That might be slow, or we could use a bitmap. We'll see both of these. And then ultimately, we need a way to structure the files. I mean, what the heck is a file? It's not a block. It's a bunch of blocks, right? Which blocks? Well, it's a good question. So we're going to call this a file header, and ultimately it's going to be called an inode. And that's going to be a word that you'll have before the end of the lecture. But basically, it's going to track which blocks belong to which offsets within the logical file structure. And we're going to optimize our block placement to try to get good performance for our usage patterns. So this is kind of where we're going. And you could make many different file systems. And how many file systems are there? Many. That's because people made many different ones. So every file system that you could use has advantages and disadvantages. We're only going to talk about a couple of them. But how many people here actually use Linux on a regular basis? Okay? With Linux, you have many file system options. Okay? How many people use Windows on a regular basis? Okay, with Windows, you probably have maybe two, and if you work really hard, you can get some of the other ones. All right? So your operating system kind of sort of impacts what you can use. But so what are these components? I'm just laying this out graphically. We start with a file path that gives us something to look up in our directory structure, which is ultimately going to give us what we're going to call a file number, which is really just an index into a file header structure, which will then find us this file header, or inode will be the term we'll use in a moment, which will then tell us which disk blocks are part of the file. So pretty much this very simple diagram is all we need to know. And what's a file system What's the difference between different file systems? It's how are these blue things structured? Okay? Any questions on this? Now, going back for a moment to this cloud storage comment that came up at the beginning of the class, this directory structure is the thing that's kind of under a lot of change of late because the number of files that you have access to is so large and it's so easy to just lose them that the idea of one global file path that every file you own is in is kind of almost an outdated idea because it's just too hard to remember where things are. And so people are starting to really replace and throw out the idea of a traditional directory structure with more like a database that you can search attributes on. Okay, and there have been many false starts, and then there's things like you can do Google Desktop, and everybody's got a desktop that helps you find things, right? And I haven't found one of these I really like yet, but it is a way to get around the file path notion. But we're going to continue with file paths for this lecture. So what we're going to do is start with a file name, go through the directory to find a file number, which will give us which blocks are of interest. And open performs an actual form of name resolution, which basically translates a path name into a file number, which is going to be our index to locating blocks, okay? And it's going to create a file descriptor in the process control block in the kernel, and then return a handle, which is an integer, to the user process. And that integer that the user process gets is per user, and so their file handle, the file descriptor, is basically unique per user, but it's then going to map into file descriptors internally, which are the actual thing the operating system's tracking. And then read, write, seek, sync, all of these things are going to operate on that handle. Okay? So here was a directory structure from David Cullers, kind of looking at this. This was off of his laptop. You guys all know these kind of graphical things, but what this is showing is this idea that there is this hierarchical naming scheme of files. And so when I talk about turning a path name into a file, we're really talking about taking something that is essentially a string descriptor of this and turning it into the actual file number that lets us access the blocks. Okay? And are there any questions on what a directory is? Because we're going to then proceed to completely ignore directories until the end of the lecture. Okay, so simply a directory is a way of somehow turning a name into a number which is going to help us find our blocks. And what I want to do next is really structure the files themselves, and then what we'll do is we'll say, well, a directory is really a file with the following structure to it. Okay? Everybody with me? Good. So, all right, we just said this. It's a hierarchical structure, and so on. Okay, so once we have, by the way, our lookup process, which we look up a name and get back a handle, that's basically where we're at here. Once we've got the handle, then we can actually access the file structure, and that's where we're going to go with this. And so the thing that came back from open was a file descriptor, which is a handle that will now let us access things. So what's a file? It's a named permanent storage. It contains a bunch of data, which are blocks on disk somewhere. And it's got a bunch of metadata, like attributes. You know, who's the owner? How big is it? When was it last opened or written? What are the access rights? Owner group other in Unix. In Windows and other somewhat, Windows is actually much more enlightened when it comes to access permissions because you have access control lists rather than this rather restrictive owner group other, which has 9 bits associated with it. In a Windows system, you can actually give arbitrarily complex control to an arbitrary set of people, and it's pretty powerful. Okay, so that's actually kind of nice. There was one system called Andrew File System from CMU that also had a full access control to it in the Unix domain. Not used as much anymore. Okay, so let's start with how do we structure a file. And I want to show you. So we haven't really talked about anything about how these data blocks are laid out on disk, and what I want to start with is something called the File Allocation Table, or FAT. And the nice thing about the FAT scheme is everyone here has used this many times, no matter what operating system you use natively. Why? your flash little USB cards. Actually, there's one up here that somebody forgot. This has probably got all sorts of interesting stuff on it. Shall we check it out? But a flash device typically is a FAT file system on here. Cameras have FAT file systems. Pretty much anything that's of the smaller exchange with any system kind of variety is often FAT. Okay, and this was originally developed for MS-DOS way back when. And we're going to assume now that the directory lookup structure exists, and so we're going to ignore how we do that. And so disk storage is basically just a collection of blocks, like we said before. And what are we going to do? Well, here's 3 blocks that might be some file. Okay, so this is, this is your data that you've been working on, for weeks. And it's in 3 blocks. Each of them maybe, let's say, 4K a piece or whatever. And the question is, how do we tie those together into a file? Because if you notice, it's sort of like, well, there's a couple of blocks up high and a couple of blocks down low. And notice, by the way, that I've numbered the blocks from 0 up to n-1. And so these 3 blocks are scattered. They're not sequential. How do I associate them together? That's a file system question. What does the file system do? Now, before we go there, why might these 3 blocks not be next to each other? That's right. There could be other data here, or maybe there was data there when we wrote this and now there isn't, or whatever. But there may be many reasons why this is fragmented this way. But now we want to tie this together, and that is what the file allocation table does. And so, for instance, suppose that we're interested in reading file number 31, block 2, offset X, whatever that is, call it byte 3. What we need to do is somehow find this block and go to offset X to read it. And how do we do that? Well, we index into the file allocation table with the file number 31. So this file number basically is position 31 in the FAT table, and that is what I got back from my directory. Okay, so I looked up super secret data in my directory, and it gave me back 31. Okay, and that 31 is coincidentally the very first block number on the disk of the first block of the file. And then what FAT does is it just links them together. Okay, and then once we've followed the links, then we can read off of the disk into memory. Okay, so basically all the file allocation table does is it is a set of links that link together either files or, I'll show you in a moment, free data. Okay, questions? So basically, FAT entry number 31 links to 32, which then links to whatever this is down here, and that's how I find all the blocks off my disk. And that is the function of the file system, is basically to do this level of organization and to maintain the FAT table based on your read and write patterns. Okay? Questions? Yeah, go ahead.
Why does the FAT table, I guess, have that separation between the second and third?
Oh, well, notice that the FAT table basically has one entry for every disk block. And so the fact that the disk blocks on disk are separated means that the links in the FAT table end up being separated. Okay, so this link here for 31, this is says probably 32, which points to this guy, and this guy says, 71. And as a result, just by tracing my way down here, I can find block number 2. So I go, I'm on 0, I find 1, I find 2, poof, I did a read. Okay? Questions? Any other questions? Good. Yeah.
Does that mean 32 is the file number of the second block?
No. That's a good question. Is 32 the file number of the second block? No. I would say, in this particular structure here, there's far less file numbers than blocks. The file numbers are really only the valid starting positions of files. So 32 in this instance isn't actually a file number, it's a block number. Okay, so the only file numbers that are valid are ones that are actually in directories that you can get by a directory search. Okay. So, let's look about some properties of this. So as we said, a file is a collection of disk blocks. The FAT is linked one for one with every block. And the file number is the index of just the root of each file. So there's only as many file numbers as starting files. And so we can talk about offsets in the file as being a pair of a block number and an offset within the block. So again, if we had 4K blocks here, then this X is from 0 to 1023. We follow the list to get the block we're interested in, and unused blocks are in a free list. So for instance, we have a free pointer, which basically links all the free blocks. Okay, and so now you've pretty much seen the good and the bad of FAT. Okay, can somebody tell me the good of FAT? Tastes good. No, that's not what we're talking about here. What's the simple? Simple. Simple. And another few of them, right? You can't get much simpler than this. What are some really bad things about this?
Use linked lists, so like if you want to get to the very end, you have to just
So first of all, this is clearly requiring linear search through this FAT table to find anything, right? This is why, by the way, that nobody in today's world ever reads the FAT off of the disk while you're looking up a file. You always read the FAT into memory first, and then you traverse it in memory. Okay? What else is a problem here? What if the FAT table gets corrupted? Go ahead. Yeah, I mean, this fragmentation here is pretty clear problem right away, and you have to basically go through and rewrite every file to unfragment it. Anybody here ever run the defrag program on like a Windows box? You know, this is something, it's like, oh, it's really late. Okay, I'm going to get my cup of coffee and I'm going to defrag. And oh, yep, that hole got filled. Yep, let's move those files around. It's actually kind of addicting when you're too tired to do anything else. You can sit and watch fragmentation. I don't know if you want to do that at parties, though. I think you'd probably lose everybody. So let's actually look what happens with a file write. So here, if I want to write to this, and I want to write block 3, what do I have to do to write block 3? Well, first of all, there is no block 3. So I have to take the free list, allocate a free block off of it, and then link it in, and then I can do my write. Okay, so there we go. All right, you have just basically seen what there is about the FAT file system. Now, actually, let's do one last thing. Let's create a new file just for the heck of it. So I free a block up. I create a new file number, which I'm going to put in some directory somewhere. I write the first block. I allocate a new block. I allocate the second block, and poof, I'm now done with writing 2 blocks. Okay. So this was used in DOS, Windows, thumb drives, pretty much everything. Where's the FAT stored? Basically on disk, in a well-defined place at the beginning of the disk. What happens when you format the disk, you basically zero all the blocks and link up the FAT and as a free list and so on, and you're good to go. Very simple. Okay, yes? Say that again? Oh, if you have a file that's less than the block size, you end up wasting it. So this is it got internal fragmentation problem. Good question. Any other questions? Okay, so what's the assessment here? The time to find a block in a large file takes a long time because you got to walk through the FAT. So this is basically bad for random access. The free list is just a bit vector in many cases. In other file systems, in the FAT, it's linked, so that's a problem. We might be able to use some sort of next fit algorithm to try to do locality in this, but oftentimes it doesn't happen. Notice that we have no prescription about how files are laid out here in the basic FAT arrangement. So there's nothing in this layout that says that I can't be more clever about how I lay my disk files out to get more locality. It's just that typically it doesn't happen in this file system. I could try to make all of the blocks sequential if I wanted. Is sequential access good? No. Random access good? Well, sequential access is not bad. Random access is bad. Does it handle fragmentation? Well, no, you get a lot of fragmentation. Does it handle small files? Well, ones that are smaller than the block size, you waste things. Does it handle big files? Well, I guess it does, but you got to walk a long way, and so on. So that basically, there's lots of limitations, and it's why pretty much people who care about storing data in a more reliable and efficient way don't use the FAT file system. It's typically used for just these little plug-in drives. All right, let's take a break, and then we'll come back and we'll talk about some better file systems. All right. Let's continue a little bit. So one of the things we could ask is, what about directories? So a directory is just a file. And so if you think about a real FAT file system with much larger file numbers, home/tom is actually just a file somewhere, and then you go to that file and you start searching through the file linearly until you find, let's say, music. So /home/tom/music is file number 35002320. So this is pretty typical situation where files are a container that can contain data, or they could be used for directories, and in the case of the FAT file system, very simply. Okay? Excuse me. All right? And so essentially, it's basically files containing file name, file number mappings, and free space for new entries or where files have been deleted. And it is kind of interesting that the attributes are actually kept in the directory rather than in the file itself. So if you sort of have any properties of the file that you care about, how long it is and so on, you actually go to the directory. And so if something happened with your directory, but you still had access to the file, you've just lost all your attributes. So this is kind of an interesting sort of problem. Every directory is a linked set of entries. Okay. So where's the root directory? Pretty much anywhere convention allows you to have it, but it turns out in FAT it's basically the first file in the system. Okay. So what about, let's look at the directory structure here for a moment. So how many disk accesses? This seems like this could be a problem on a midterm at some point, right? /my/book/count. What do you have to do? You read the file header for the root at a fixed spot on the disk. Then you read in the first data block for root, and it's a table of file name pairs. Hopefully you find the word my very quickly in the first block. Then that points you at the my directory file, and then you look up in there, you open it up. First data block for my, you search for book, and then you open the book one, you search that until you find count. Then you read in the file header for count, and then at that point you can finally read the file count. Okay, so notice there's a bunch of resolution. This is called name resolution, where I'm going through and I'm turning the path into the final file number of the file I want. Okay, and does everybody see how I've gone through a bunch of directories? I've gone through the / directory, the my directory, the book directory, and then I found the count file. So there's many directory lookups there. Is everybody with me on that? And so you could count sort of how many disk accesses are involved there if you were so inclined. Now, of course, one of the things that is very useful in all of these schemes is what's typically called the current working directory, which essentially is associated with a process which says this is the current directory that we're thinking is the locale for access for that process, and that could be, for instance, /my/book, and at that point I could resolve count by just looking at that directory. So that's what the current working directory is. When you do CD to something, you're changing to the current working directory. Can anyone, by the way, come up with a way of avoiding doing this too many times? I mean, what if /my/book had 1,000 files in it that you had to open? Would you go through this resolution every time? Well, you could CD, I guess, the current working directory. What else could you do? Yeah.
Some sort of equivalent to like the TLD.
Yes. Who said that? Cache. Yes. Exactly. So you can use a name cache. By the way, remember how I said most of the topics in operating systems are about caching? Woohoo! Name caching. There's one. Now, what's the danger of a name cache?
What if you say change names or something?
Yeah, what if you change the /my/book directory to be /your/book directory? I've just moved the name, and now all of my cached name references are broken. So if you're gonna have a cache of names, you better make sure it gets invalidated when you change something. Okay, good. All right. So there's a lot of security holes in FAT. So first of all, there's no access rights. So I could read this drive, whoever's this is, and hopefully there's nothing too sensitive on there. There's no header in the file blocks. Okay, so that's potentially problematic in that I can't keep attributes with the actual file. I have to put them in the directory. Basically, I just have an index into the FAT, and file number is block number. So basically, I could read in the middle of a file just by randomly picking a file number. Okay, there's no restriction on that. You could screw somebody up by breaking links. I mean, there's all sorts of things you could do, right? So the FAT file system is not for secure access. Okay. All right. So you might ask, why does everybody use it? I guess it's simple and historical. And it doesn't have a lot of overhead. So now I wanted to switch gears to see what we could do that's better. And we're going to continue this discussion on Wednesday, but what are some characteristics of files that people really use? And this is an example of a study from 2005 that looked at things like how big are files and how big are directories. And what they saw is that most of the files are small, but most of the space is occupied by a few big ones. Okay, so big files take up all the space, but the directories are taken up by small files. Okay, so whatever we do, ideally we have a system that handles small files really well, but also handles really big files. And of course, a new constraint that we all know about is multimedia being the thing. We better make sure that these big files can stream efficiently, sequentially, if nothing else. That's going to be important. Large sequential streaming of files is important. So let's look at a real file system. So here is something that we're going to look at in a moment. This is actually the indexed file structure that started out in BSD 4.1 and is used in a lot of systems these days. So basically, what is an inode? An inode is this structure that describes the file, and typically the file number that we've been talking about points into an array of inodes. And so now, unlike the FAT file system, which was a little confusing because of that, I realize, every one of the file numbers means something. Every one of them is an inode. Okay, this is an actual array. And if I know what the file number is, I look up the inode. In that inode, describing the file is everything like its metadata, permissions. Is it, can you read it? Can you write it? When was it last written? All that stuff, plus pointers to a bunch of blocks. That's an inode. Okay? And we'll talk about the actual, what these things are. But the Unix fast file system, which is became basically ext 2 and 3 and is used by lots of people in BSD and in Linux, basically was the original inode format. It appeared in BSD 4.1. And by the way, I don't know if you know it, but your heritage here at Berkeley is about the Berkeley Standard Distribution, among other things, which was sort of the premier Unix system that first got really cool file systems, and the first system to have sockets on it as well came from Berkeley. So that was a research system that apparently with each release that came out, there were runners from companies that were waiting for the tapes of the new system to come out, and they would grab them and they would take them off to the companies. So this was had a lot of hype attached to it. So BSD is something to be proud of. Go Bears. It's in this particular system, basically the file number is an index into an inode array, as we mentioned. This is a multi-level index structure. I'm going to show you this in a moment. Unlike the FAT file system where there was a single linked list, this one has multiple levels to it, and there's good reasons for that. It's great for both little and large files. That's kind of where it was targeted, and it's an asymmetric tree of blocks. The metadata is actually associated with the file itself rather than being in some random directory structure, which is going to be important because if you think this through, it's very important for the object, namely the file, to be separated from the naming structure. How do I name it? Slash, my, slash book, slash count. That's a name. The actual file itself is self-contained in the BSD file system, and I could name it any way I want. If I can come up with a file number, that's good enough. Okay, and I could put that in a database, whatever. So this is separating naming from the object. All right, and the Unix fast file system, which, by the way, I forgot to. I'll put this up later tonight. There's a good paper on all of the optimizations that went into the fast file system. Was really the 4.2 release, where in order to make the 4.1 file system perform well, they put in all sorts of locality heuristics and so on. So 4.1 was the original format. 4.2 was allowed larger files and had better locality to it. Okay? So the way you're going to want to look at what I'm about to show you is we're going to separate correctness from performance. Okay, just to throw out a couple of generic high-level terms to you guys. The correctness is going to be about structuring the file system in a way that's able to deal with both small and large files and metadata well. Performance is going to be about, under the covers, being able to make sure that we've got good sequential strings of blocks to get good performance when we need it. Okay, and we can do that performance underneath the actual file structure. And in principle, we could do this with the FAT file system. but it doesn't really give you a lot of opportunity to optimize performance other than sitting and watching it rearrange blocks to remove fragmentation. Okay? And it has a very scalable directory structure potentially as well. So here, before we do the actual thing, I wanted to say a little bit about the PNTOS file system, if you're feeling so inclined. And at Stanford, the fourth PNTOS lab is a file system. You can go and take a look, and rather than this more complicated thing, what you can look is you can see that, well, a file is actually has an inode associated with it in a position, so that sounds pretty close to a descriptor that we talked about. If you look inside the inode, you'll actually see there's a bunch of metadata plus some data inode pointers. And if you look down way far into this, what you're going to find is that the only type of file you're allowed to have in the default PNTOS file system is a sequential set of blocks starting at one point and going for some number of sectors. That's the default file system allows only files like that. And of course, what the lab is about is turning this into a real file system. Okay? But you can think that the disadvantage of that is you've got to find a big enough hole for the file you want in order to make it fit, right? Everybody see that? That's kind of a disadvantage. You can't really deal with a fragmented file in that sort of file system. So that's why, in fact, the fast file system looks more like this. So the inode structure in this metadata area says what user owns it, what group it's part of, the 9 access rights, which you guys are used to, read, write, execute for user, group, and world. These are all things that you know about, but a couple of things you probably don't is set UID and get GIDs. Anybody know what these are? What's the set UID bit do? So when you have set GID on a file, what it says is it doesn't matter who you are that's executing this file, it will run with the permissions of the owner. So you should take a look. Some of those, some of the things that you might normally run, like PS and what have you, are actually set UID because they become root when you run them. It doesn't matter that you're you; they become root as you run them, and then they run with root permissions. And that's because the root user has designated that that's okay and set the set UID bit on it. Okay. You can imagine all of the security holes associated with this. There's also a group version of that. If you look further in the inode structure, there's a bunch of direct pointers. The direct pointers are pointers to disk blocks. So in this, the 4K disk blocks, every pointer points to an actual disk block, and there's 10 of these typically. 1, 2, 3, yep. Okay. And maybe that's 12. But they're pointing at direct blocks. For higher numbers, basically we have what's called an indirect pointer, which points to a block of pointers. Doubly indirect points to a block, which points to blocks of pointers. And then triply indirect points to points to points. Can anybody tell me why we have these complicated structures? Why would we have the direct pointers, the indirect pointers, doubly indirect pointers, and triply indirect pointers? Yes?
Deal with large files, which are relatively rare and still maintain good performance for small files.
Right, perfect. So this is to deal really well with small files, but still be able to do well with large files. Everybody catch that? For small files, we only have to look up the inode, and we have the direct pointers to the first blocks. If we have really big files, what's probably true about a really big file is that A, we're going to be accessing it sequentially. Remember we said that earlier, maybe. And we're going to do so with enough time that the file system can easily read these intermediate blocks, and so the overhead of reading these blocks doesn't really get into the access time of the access very much. Okay, so this is a structure that deals well with low and large and small files. And if you look, the direct pointers here handle kind of the lower part of the curve in terms of file size. And then the indirect pointers basically allow you to get up to 4 terabytes of storage, and they kind of deal with things in the middle here. And then for the really long tail, fast file system may not be able to store your data because it may not have large enough file sizes. Okay? Questions? All right. So let's talk a little bit about free space, and then we'll continue this next time. Basically, the nice thing about everything, all the blocks being the same size, is we can use a bit vector with a bit per storage. And this is stored at a free fixed location in the file system as to which blocks are free. We can also talk about where the inodes are stored. In the early Unix and actually DOS, Windows FAT file system, the headers are actually stored in a special array on the outermost cylinders of the disk. Okay, so basically that inode array is on the outside. What's the downside of that? Yeah, so you have to go out to your inode, back to your block, right? So there's a lot of seeking involved. Great. What else? So it's a performance problem. Anything else? Yeah. Yeah, actually, the reads on the outside are actually faster, but it's the reverse. So there's also this interesting thing that you format a fixed number of inodes at the time that you format the disk, and it's actually possible to run out of inodes. Actually, we did that on our server, right? I think our server, when it was dying, we were running out of inodes. But yeah, so your fixed number of inodes, no matter how many files you've got. The real problem here, which we'll talk more about next time, is if you get a disk head crash that happens to toast the outer cylinders, you've just lost access to all of your files because you've killed off the inodes. Right? That's a really bad from a reliability standpoint. And so newer versions basically do the following. I'm going to show you this picture. They basically group things into block groups. They spread inodes throughout. Every block group has an inode array, and the inode arrays relate to files and directories in the given block group. So they've addressed both the locality and the reliability in kind of this one layout. All right, so let's finish up for now. In conclusion, we talked about file systems for transforming blocks into files and directories. They're going to be optimized for access and usage patterns. We'll talk more about that next time. There's a header called an inode that defines files and directories. This multi-level index scheme we've been talking about is the one we really want to use, and we're going to talk a lot more about that. And we're going to, in fact, talk about optimizations for the 4.2 BSD scheme, and we'll talk about NTFS and a few other things next time. So I hope you have a great Monday night. We shall see you on Wednesday. Don't forget to get your regrade requests if you're going to do it in by Thursday.